Gosh, I wish I had to wipe down all these medical device screens.
What if you get a universal robot? It can do the wipe down action for you.
What a great idea! Having the UR to do the wipe down action is better, but setting waypoints for each corner also takes a good amount of time.
What if we integrate a vision system to give the UR eyes? Then we wouldn't have to manually set the waypoints ourselves. The vision system can find them and set them for us.
Let's get to researching. Based on the research for the vision system and UR, we came up with some design constraints. First, there's performance. The robot must be able to perform a clean/swiping action with minimal user setup.
Next, it must be modular. The software must be written in a way that allows for additional motions, testing procedures, or object identification code blocks to be easily added into the software at a later date.
There's scalability and adaptability. The development of the software must allow for future code to be easily added in without need to understand the parallel code components.
And lastly, it must be compatible. The developed software needs to be compatible with the UR robot and its platform in order to function.
Our system includes three main programs. The Python vision system handles the machine learning, computer vision, and camera control. The URCAP and URScript on the universal robot provide the user interface and controls robotic movements. The server connects the vision system and the robot, managing communication, errors, and shutdowns. The server listens for requests from the vision system or UR. Each request starts with one of 6 keywords, triggering actions like sending data, updating variables, or handling errors.
The Python vision system captures images using the camera and analyzes the images using machine learning and computer vision. The machine learning is only used for classifying the captured images and determining the next step. Further analysis is done entirely by computer vision. If the image does not contain a screen, information is sent back to the UR system, indicating a camera view change is needed.
Once a workable image is provided, the computer vision software will run it through a series of thresholding and image processing steps, including a complex thresholding step, edge detection, and corner identification. Once the critical corners of the object are identified, the movement vector can then be determined via the mathematical code, allowing the robot to reach the designated action point.
With all the programs test ready and the necessary requirements for the camera, we can now set up our testing system.
Since we don't have constant access to a UR, a gantry system that works in a 6-axis coordinate system was built to test the machine learning and vision system with the camera.
The gantry is manually operated for testing, allowing an operator to simulate the reach, flexibility, and stability of a universal robot. Our goal is to simulate the consistency of robot-aided movement with the external noise of a realistic system.
As we can see, the gantry system is particularly helpful to test the computer vision software due to the fact that it can move in the 6 axes just like the UR robot can. This is a benefit to the project because we do not have access to the UR robot for the entirety of the project and offered us a chance to test the functionality of the mathematical code.
For the development and testing of the Java server and URCAP, a simulated UR was used to test connectivity and robotic function. To make sure that the design is applicable on a physical universal robot, a UR10 was provided at Stryker's facility to test the communication, remote movements, as well as performing the specified wiping action.
While both the Python vision system and the Java server are tested using the sponsor's UR, this was simply to prove connectivity was possible.
Now the testing done with our gantry system and the live UR, let's go over some of our accomplishments. There's the UR cap. The UI allows for the setup of the testing process. The UR can be remotely controlled, and a wipe down tool can apply constant force to a 2D touch surface.
Now looking at Java, the server allows the setting and receiving of different variable types. Looking at Python, machine learning can accept, classify, and output classifications of image data. It can also send proper clean images to the computer vision, which the computer vision can then take and threshold. Computer vision then outputs a movement vector in the X, Y, and Z directions. It still needs more additional testing done with the X, Y, Z angle changes.
Overall, more testing needs to be completed between the code communication and a live UR. We want to thank our sponsor, Stryker, our sponsor representatives, especially Kevin Van Dyke and Stephen Burkhart, our advisors, and our senior design TAs. Thank you for watching.